Hello. Today I'd like to discuss a little bit about elementary row operations and equivalent systems of equations. And to start with this discussion, I would like to say the following in terms of the definition. Let S1 and S2 be systems of linear equations with the same associated unknowns. And we say that S1 and S2 are equivalent if they have exactly the same solutions, meaning that if you find a solution for S1, that is a solution also for S2, and a solution for S2 should be also a solution for S1. Now, the thing is that the question is, how do we transform solutions in one system? I mean, how do we recognize solutions of one system being a member of another one? For that, we have the mechanism of applying elementary row operations on the augmented matrix form. And why is that? Well, because those operations that I'm indicating here by swapping rows, multiplying by a non-zero scalar, or adding a constant multiple of a row to another, well, they all indicate an operation that doesn't affect the nature of the solution to a system. In other words, if you swap any two rows or any two equations equivalently in a system, well, you don't alter the solutions to that system. If you multiply one of the rows, meaning multiplying a whole equation by a non-zero constant, you don't affect the solutions that you obtain or that are pertaining to that system. And in the same fashion, if you add a constant multiple of an equation to another, meaning a row in this context, well, you don't affect the solution set to that system. So, what is that we're going to do? Well, we're going to clarify, we're going to explore it in terms of system of equations first, and then transform this question into a problem of matrices, perform a series of reductions until the solution is very clear for us. So we'll start in this fashion. I'm going to label this as S1. This is my first system, right? But of course, I don't really want to work with the equations as we have seen that working with matrices is much more efficient, as we only have to keep track of the coefficients associated with the unknowns. So we'll start by making a transformation here. So I'll create a matrix, a rectangular array of numbers. So 2, 6, 2, 4, 1, 1, -1, and 1 for this one. Here, there we go. We have our augmented system. We have the association x, y, z constants to the right of the equations. And then we proceed by applying these operations that, as we said, do not affect the solution set. Right? So they leave it invariant. So the first operation is I'm going to multiply row number 1 by 1/2. So I'm applying an instance of this operation, right? In this case. So the result of that is the following. I have 1, 3, 1, 2, and the second row remains unaffected, so it's just 1, 1, -1, 1. Next, what I'm going to do is I'm applying the idea behind the Gauss-Jordan elimination process. So I'll select this as a pivot, and then once I make that selection, I'll eliminate every single entry on that column that is not a pivot. In other words, that results in, or that can be achieved by applying the following operation. To row number 2, I subtract row number 1. This is an instance of the third type of operation. Why? Because to row number 2, I'm subtracting or adding -1 of row number 1. Now the result of that is the following matrix. I have 1, 3, 1, 2, 0, and -2, -2, -1. Okay. Next, well, what I'm going to do is, now that I have eliminated everything on this first column, well, I move to the second, following this staircase pattern, and select a pivot. So I'm going to use this as a pivot, but in order to make it a pivot, I'll have to multiply the second row by -1/2. making an instance of this operation one more time, right? So I'll signal it here as negative 1/2 of row number 2. And the resulting matrix looks like this. We have 1, 3, 1, 2, followed by 0, 1, 1, negative 1/2. Right. Okay, we're almost done. Now this is a pivot, and we could use it to eliminate everything that is on the remaining entries on that column that we're currently working. So next operation, it's to row number 1. I subtract 3 times row number 2, and the result of that, it would be 1 on this entry, 0, negative 2, 1/2, followed by 0, 1, 1, 1/2. Now, we should recognize that at this moment, what we obtain is the row reduced echelon form of the original associated matrix. Now, this means that in terms of the Gauss-Jordan elimination process, we're finished, right? This is the termination phase. So now it's time to recognize the nature of the system. Probably it's much easier now to read, because from here we make a conversion. We say, okay, well, look, whatever we have here actually is stated in this fashion. So I have x minus 2z is equal to 1/2. And I have that y plus z is equal to 1/2. Of course, I can write this into an equivalent form that is might be a little bit much easier to read, which is that where we leave the unknowns in terms of, well, the one that appears on both expressions. In other words, I'll write this as x equal to 2z plus 1/2 and y as a negative z plus 1/2. And note that z is unconstrained. So we may use it as a parameter. So a parameter for what? Well, a parameter to indicate all solutions across this solution set. So I'm going to write it. If I have a solution of the form x, y, z, well, that has to have the following form. It has to be 2z plus 1/2 minus z plus 1/2, z plus 0. Of course, I can write this as z times 2, negative 1, 1, plus 1/2 times 1, 1, 0, right? If you choose to write it in this particular fashion. Now, let's check, right? At this moment, I'm going to label this as S2. My claim is that S1 and S2 are equivalent systems. Of course, we may say yes, because they were obtained by applying these elementary operations on the equations themselves, or of course, disguided or kind of as if we were just seeing them in terms of matrices, not in terms of equations themselves. But let's see. Why don't we check? Well, what is indication? S1, right, as stated right here, now looks like this. Well, what is x? Well, x should be twice x would be 2z plus 1/2 plus 6 times y, but y is negative z plus 1/2, and then plus 2z. But then after a reduction, we realize that this is actually 4. So it checks. For the second equation, we have 2z plus 1/2 plus y, which is negative c plus 1/2 minus z, which turns out to be, well, exactly 1, and it checks. So that, what does this mean? Look, the solutions for the system, which are much easily reproducible, actually are the ones that are solutions for this. In other words, we just showed by this verification step that every solution to S2 is a solution to S1. So how do we know that every solution to S1 is a solution to S2? Well, by simply following the indications that we have on every single step n in this reduction process. So, well, that's it. With this, we finish. I hope that you like it. Take care.